Hey class, lab 3 is the contribution of energy systems in a Wingate test. So a few things that I wanted to talk about before we really get into this. Um, Certainly pause and go ahead and read this document posted on Canvas. But I'm going to talk about two things before I start messing with Excel, uh, and hopefully you'll follow me along. So, broadly, our bodies use three separate energy systems to create something called adenosine triphosphate. So, whenever you eat food, you actually break down carbohydrates, fats, and sometimes protein into adenosine triphosphate. And hopefully, we're getting close, or we've already spoken about the bioenergetics lectures. And if we haven't, all you really need to know is that we have three different systems for making adenosine triphosphate, or ATP. So this first one being ATP PC, that stands for phosphocreatine. So if you've ever heard of creatine or creatine monohydrate, that's a supplement that might have something to do with this. So stay tuned. We'll talk about more in class. Next, the glycolytic system. So just kind of how we break down glucose mainly for energy. And then lastly, the aerobic system. So those are our three main systems, how we actually make energy for our body. But in class today, we're going to be doing a Wingate test, which is just a test of muscular power. It is 30 seconds long. We put on 7.5% of an individual's body weight onto the Monarch bikes that we have, and you just cycle as quickly as you can for 30 seconds. There's the protocol and like procedures over here, so pay attention to that. One person in each group is going to do this twice, and we're actually going to look at fatigue over time. But this Wingate test, there are uh, there actually is some research that figured out the relative energy contributions of the ATP PC, glycolytic, and aerobic systems during this 30-second test at each 5-second time frame. And where is that paper? It's actually right here. Pretty cool paper. So contribution of energy systems, Jimmy Smith, David Hill, really cool. And look at that. University of North Texas, Denton, Texas. That's actually the town I grew up in, so it's pretty cool. I'm going to post this paper on Canvas too if you want to give it a read. How I derived these numbers was really just by following along with these values. So here's the contribution ATP-PC, glycolytic, and then their aerobic. And if you want to check me on some of that, you certainly can. However, I probably did it close enough. Um, all right, let's get back to the document. Really cool stuff, but we're going to look at um, the relative contributions to every 5-second time point in here. But first thing we need to do, we need to make our Excel document. So you really need to make this before class so that, well, it'll just be a lot easier if you actually do it this way. So go ahead and pause the video right now and fill out all of this so far, and then we're going to start putting in calculations together. Okay, so I paused for a second, and hopefully you paused and you started writing all of this stuff out. So here, let's start at the top. So body weight, LBS. Really quick, let's just say that someone weighs 165 pounds. That's, I don't know, kind of the standard that we normally do. Here, body weight kg. Let's just convert that really quick. Press the equal sign, highlight that cell, divide by 2.2046. Hopefully everyone's getting tired of that by now. Oh, I already had that one entered. Sorry, didn't mean to do that. Um, so here we go. Body weight in kgs. So 165 pounds is close to 75 kgs. Now I said that we're going to have 7.5% of an individual's body weight on the bikes. So let's do that. Equals this in kilograms multiplied by 0.075. That's 7.5% right there. So if an individual weighs 165 pounds, they're about 75 kilograms, they will need about 5.6 kilograms on one of our bikes. And remember, the tray already weighs 1 kilogram. Now, one thing that we have to do, because we're going to be calculating work and power, really just power, but we have to convert this value to newtons first. So, equal sign, highlight that, multiplied by 9.81. So that's how many newtons are on there. And right here, just for calculating distances, meters per revolution, everyone is 6 meters. So good, there we go on that. Now, something that you're going to be doing, you're actually going to count how many revolutions happen in every 5-second time frame. So in your groups, one person is going to be keeping track of time, one person is going to be running the test, and another or two other individuals are actually going to be calculating the revolutions for the first 5 seconds, the next 5 seconds, and so on and so forth. And whenever you count this, it's important to always start at 0. Otherwise, it's really not going to work at all. So let's figure some of this stuff out. Let's say that you do 15 revolutions in the first 5 seconds, then it goes down to, I don't know, 13, then 11, then 9 revolutions, 7, and then in the last one, let's say 5. So here, let's just calculate the total revolutions that were done right here. So equal sign, write the word sum, S-U-M, open parenthesis, highlight all of these numbers, close parenthesis. There we go. We added all of that together, 60 revolutions. Some of the stuff that you're going to have to calculate are powers at each one of these time points. So here's how we do that. So here equals, we have to multiply the force in newtons. So right there, weight in newtons, or force in newtons is probably what that should say. Weight in newtons multiplied by the amount of revolutions that we did, multiplied by the meters per revolution, right there. Another thing that you're going to have to do, since this was in a 5-second time frame, you're going to have to divide this number by 5. So just click on that and divide by 5. Enter. There we go. So in that first 5 seconds, we're generating here power. Let's put that in watts just so that everybody knows. 991.19 watts right there. So that's what that is. We're going to have to do this for every single one of these. So here, let's go ahead and do that. Equal sign, newtons multiplied by amount of revolutions multiplied by that divided by 5. Each one of these is divided by 5 equals newtons. Hopefully I'm doing this slow or fast enough for you that you aren't hating this video. Almost there, just got a few more to do. Two more, almost there. Divide by 5. There we go. And then the very last one. Well, I mean, you could do that. Order of operations doesn't really seem to matter. Uh, there we go. Right there. Okay. So something else to make this look a little bit better, let's just reduce uh, the amount of decimals right there just so it looks a little bit more clean. All right, good stuff right there. Okay. Now we're going to start calculating the relative amounts of like power generated by each one of these energy systems. So I already had this set up for you. You don't have to calculate uh, any of these percentages. So here, let's go and do that. Okay, so equal sign that, and then multiplied by, if you entered this as a percentage, it should be good. You just click on that, enter, excellent. So right here, I'm gonna go ahead and highlight all of these as well, just so that they don't go too many decimals. So right here, 92%, 991, 911 is 92% of 991. Good stuff right there. Perfect. So how can we do that? If we drag this across, check that out. Okay. How I did that is I just grabbed this part right here and I just drug it straight across, and then that's going to do that calculation for us. So here, 40% of 859 is 343. Pretty cool stuff. So all these 0%, like that's fairly easy to do. So let's go ahead and do the rest of this. Equal sign right there, the power multiplied by glycolytic. There we go, 79. Great, great stuff. And then here with the aerobic, equal sign, that power multiplied by, well, in this case, 0. Enter that. Have that go straight across. Good stuff. And here, let's reduce those just a little bit. Fun stuff there so far. All right, we just calculated the amount of power from each one of these energy systems in like this hypothetical condition. So next, what we need to do is enter the total amount of power from all of these energy systems. So how we do that, equal sign, SUM, open parenthesis, highlight that, close parenthesis, enter. There we go. And then hold it over this little square right here, drag that right on down. So over the totality of this 30-second test, the ATP PC system did around 1255 watts of it. The glycolytic system did around 2100 watts, and the aerobic system did 578 watts. Pretty interesting. Some other stuff that I want you to figure out down here, we're going to have to enter some more equations for all of these. So right here, let me see if I can figure this out for us. Okay, so equal sign here for anaerobic capacity or average power, so over the totality of the test. pretty straightforward. We have to calculate or like just summate everything together. So let's click on the newtons, multiply that by right here, the total revolutions, and then multiply that by the meters per revolution, 6. Enter that. Now that looks like an absurd number, and yes it is. So we have to divide it by 30 seconds. So the average or average power over this whole 30 seconds, this individual maintained 660 watts over the totality of this. Now, how we compare this between individuals who were different body weights, we would actually divide by kilograms. So we would put enter, highlight that, divide, body weight in kg, right there, enter that. There we go. So 8.83. And if we go look, I supplied this for you over here. These normative values, you'll probably have to actually open up this so that you can see it a little bit better. So anaerobic capacity right here, let's just say it's a male, 8.83. That would put them in 8.83, just about the average category. So that's how we would figure that out. All right, let's go over here. Peak power. All this is just the highest amount of power that was held for 5 seconds during the total test. So if you remember, that's actually just this value right here. Like normally individuals hit their peak power within the first 5 seconds, but let's just go and go through that calculation one more time just so that everybody gets it. Equal sign. So here, 15 revolutions, that was their most, but we have to multiply by newtons first, multiplied by 15 revolutions, multiplied by 6, and then divide by 5 because it was over 5 seconds. Good, awesome, happened again. And with this, we have to divide it by weight in kilograms. So divide, click on that weight in kilograms, right there. Good stuff. So there we go with that. All right, 13.24 watts per kg. Let's look at where that is. So, gosh, I can hold that in my head for a second. 13.24. Sorry, yeah, I'm getting tired. Here, excellent. 13.24. That's where that is. The last thing that we're going to do is calculate this fatigue index. So what a fatigue index is just your percent drop from your highest power output to your lowest power output. So what we could do here is equal sign. Here, let me think about this for just 1 second. I also have the calculation for it right here. If if you're wanting to figure out how I'm getting all these calculations, so peak minus lowest peak value, and then divide that by peak anaerobic power, and then multiply it by 100. So let's go and do that. Okay. So first off, let's put a parenthesis. So right there, subtracted by the lowest power value, which is right there. Close that up, and then let's divide it by the highest peak value, like how we said, and then multiply it by 100. There we go. 66.67. So there's a 66.67% drop from this highest value to this lowest value. All right, all of those are fairly important things for you to do. So hopefully you made this, and certainly watch the video again if you had any difficulty with it. But awesome. See you in class. I'll explain everything else whenever we're in there.